Types of crystalline solids. So we mentioned that solids can be crystalline or amorphous. A is a prefix meaning without. Amorphous means without shape. So an amorphous solid doesn't have any long-range order to its particles. A crystalline solid is going to be well ordered. It's going to have an array of order that's going to extend in 3 dimensions, and that's why crystals have such beautiful shapes. We can divide crystalline solids into 3 categories: molecular, ionic, or atomic. And we're doing this based on what the individual units are that compose the solid. So crystalline solids we can divide into molecular solids, ionic solids, and atomic solids. In an atomic solid, the individual units within it are atoms, hence the name atomic solid. These guys are going to have variable melting points. Some atomic solids have high melting points, some have low melting points. Then we have ionic solids. Guess what they're composed of? Ions. Okay, so the composite units of an ionic solid are, we call them formula units because it's kind of silly to talk about a molecule of an ionic compound. But they're cations and anions. They're ions. Ionic solids generally have very high melting points. Because what is holding the ions together? It's ionic bonds all the way through. Ionic bonds are very strong. What's holding the atoms in an atomic solid together? It's not covalent bonds, usually. There are some that are covalent, but most of them are not. Mostly it's dispersion forces, which are weak, right? So atomic solids are the most variable. And then we've got molecular solids. The units of a molecular solid are molecules. And so these are generally going to have low melting points because it's just intermolecular attractions that are holding them together. So here we have an example. Ice is a crystalline solid. If you've ever seen snowflakes or even looked at the ice crystals that are, clogging up your freezer, you can see they've got shiny sides. They're crystals, aren't they? They have an order to them. Table salt, sodium chloride, is an ionic crystalline solid. You look at the table salt up close. It's all these little cubes. Do they do that intentionally? Do they put out a lot of effort to make your salt pretty? Little tiny cubes? No. That's just how sodium chloride makes itself a solid. It just makes crystals. It's just what it does. You'd have to work hard to get it not to do that. And then an example of an atomic solid is gold. Now, variable melting points. Some atomic solids, like xenon melts at a really, really low temperature. And yet, the metals are all atomic solids, and many of them have very high melting points. Iron has a very high melting point. So their melting points can be all over the place. I kind of jumped ahead again. So molecular solids contain molecules. These are held together by intermolecular forces, those 3 types that we just talked about. Ice is frozen water, solid water. That's held together by hydrogen bonds. Dry ice is held together by dispersion forces because carbon dioxide is a nonpolar molecule. Dry ice sublimes. It goes directly to the gas state at a very cold temperature. Ice will melt at 0 degrees Celsius, but it won't go into the gas state until 100 degrees Celsius. And so again, we see an illustration of the strength of the intermolecular forces affecting the melting points and boiling points. So ice melts at 0, dry ice sublimes at -78. But these molecular solids tend to have low to moderately low melting points. Ionic solids, things like table salt, calcium fluoride, These are held together by electrostatic attractions, ionic bonds. And so essentially, the whole piece is one molecule, if you will, because it's the same interactions all the way through. It's ionic bonds all the way through that little salt crystal. These tend to have high melting points because ionic bonds tend to be very strong. So we've got, in table salt, we've got sodium ions and chloride ions, and they're held together in a three-dimensional array by ionic bonds. Sodium chloride will melt at 801 degrees Celsius. It's really, really high temperature. And that illustrates how strong those ionic bonds are. Atomic solids have atoms, and there are different categories of atomic solids. So examples here are diamonds, iron, and solid xenon. So we can divide these into three different categories depending on what kind of force is holding them together. And the melting points of these are going to vary widely. So what are those forces? Well, we can have atomic solids that are covalently bonded together. Silicon is an example of this. Diamond is an example of this. The individual atoms are actually held together by covalent bonds. Why isn't it a molecule then? It's only one kind of atom. It's an element. So the whole thing is silicon atoms. That's why it's considered an atomic solid and not a molecular solid. So these are going to have high melting points because covalent bonds are strong. You can have non-bonding atomic solids, and these are things like xenon. These are held together only by dispersion forces. Dispersion forces are very weak, and so these are going to have very low melting points. Some things like helium, they list the melting point of helium as I think like 2 degrees Kelvin, not degrees, 2 Kelvin. You actually can't get solid helium to form at atmospheric pressure. You have to increase the pressure to 25 atmospheres at almost 0 Kelvin to get it to freeze. So helium well, hydrogen is the smallest atom, but helium is the next smallest, and its dispersion forces are just incredibly weak, and so you can just almost not even get it to stick together at all. And then there are metallic atomic solids, and these are held together by metallic bonds, and these are going to have varying melting points. Mercury is a metal that is a liquid at room temperature. And we know that things like iron and aluminum melt at very high temperatures, because otherwise we wouldn't be able to use them as pots on the stove and stick them in a flame and have them not melt. So the melting points of metals are very, very. So those covalent atomic solids held together by covalent bonds. We can think of a diamond crystal as being one giant molecule, but we wouldn't consider the individual particles to be molecules because it's just one molecule. Diamonds are estimated to melt at about 3,800 degrees Celsius. So that's crazy high. In a diamond, you have the individual carbon atoms arranged in a particular hexagonal pattern. A diamond is composed of just carbon atoms. The graphite in your pencil is composed of carbon atoms. And yet it's very different, isn't it? Graphite is soft and slippery and black, and crystals are hard and clear, right? Graphite is cheap, diamonds are expensive. And it just has to do with how the carbon atoms are attached to each other. Non-bonding, again, the weak dispersion forces. Xenon melts at minus 112. That's a low melting point. And then the metallic solids. Metallic bonds are a little hard to understand. The simplest model is we can think of them as consisting of positively charged electrons in a positively charged ions in a sea of electrons. Because we know that the metals tend to form positive ions, right? So iron tends to form a +2 or a +3 ion. So when it is in its elemental state, we can think of them as being individual ions, but then there's electrons that came from them, right? The whole piece of metal isn't charged. There are electrons. Let me see if there's a picture coming. Oh, good. Here's a picture. So here we've got something that's forming a +1 charge. Let's say, maybe this is sodium. So sodium forms +1 ions, and there's an electron that was with that atom. So this electron now, basically, I've said before that electrons, I think of them as being little boys. The electron went out to play. So he's running around the neighborhood, and there's little boy electrons from other houses running around the neighborhood. So there's these electrons that are kind of swimming around, but there's an attraction between those electrons and the cations that they came from. And there's an attraction when they move around. There's always this attraction, and so it keeps them together. So it's kind of hard to understand. So, yeah, it's an electron C. So identify each of these solids as molecular, ionic, or atomic. NH3. What do you think? Is this an element or a compound? It's a compound, right? There's two different elements. So it can't be an atomic solid. Is this ionic or molecular? Does it have a metal in it? It's molecular. So this is covalent, and we learned how to identify that when we talked about nomenclature. Remember way back then? It was like chapter 5, right? Don't forget all that stuff. It's coming back. We have two nonmetals. This forms a molecule with covalent bonds. So this is going to be a molecular solid. How about calcium oxide? That's ionic. The first element is a metal. We would name it using the rules for ionic compounds, and the kind of solid is ionic as well. How about krypton? It's going to be atomic. Krypton is an element. It's all by itself. So the individual particles are going to be atoms. So a question like this should be easy to answer. Don't make it more difficult than it is. Just look at the substance. If it's an element, if there's one capital letter, it's atomic. If there's a metal, it's ionic. If there's no metals, it's molecular. There's only one exception to that. If you have NH4, you have that ammonium ion. That probably won't show up on an exam though. But if you had NH4Cl, we need to recognize that this is an ion, and so that would be an ionic solid.